Example 11. True story. True story. The position function for a falling object on or near the surface of the moon. And by near, within 6 feet. So kind of reasonable. Somewhere in this area, we have an equation that describes the position of a falling object on the moon, where h of t is the height of the object above the moon surface in feet, and t is in seconds that have elapsed. H sub o, or h sub 0, that's physics notation, right? What would that subscript mean? It's the height at time 0, or the initial height. Yeah, height at time 0, or the initial height. All right, so part A, if you were eating at an Italian restaurant on the moon, which Yelp says has great food, but no atmosphere. And bad service. Yuck, yuck, and bad service. And your meatball rolled off of the 3.2-foot high table. Okay, so this could be you, or maybe you're next to yourself. They don't look like they're eating meatballs. But you know, when you Google pepperoni or Italian food on the moon, very few images come up, surprisingly. So you had to take what you can get. Yeah. So anyway, maybe there's meatballs on the pizza. So anyway, notice you're dressed for the moon as well. You got them space costumes on. Yeah, cool. Here we go. After how many seconds will your meatball hit the floor? Remember, you're on the moon now, not on planet Earth. How are we going to figure that out? We want to know after how many seconds will the meatball hit the floor? All we have is the height of the meatball at any given time. Let's go ahead and create an equation. The height at any given time, the instantaneous position, would be negative 2.66 t squared plus h sub o. What is h sub o? It is a constant. It's representing the initial height of the meatball in feet. Very good. We can plug it in 3.2 feet. Now there's also, you could also add v sub o times t. V sub o would be the initial velocity, but we're not throwing the meatball onto the ground. It's good food. We're not throwing it on the ground. It just rolls off. It's round, rolls, right? What do we want to do with that now? No, not yet. I want to know how long it's going to take for it to hit the floor. Solve for t. What do you mean? This is a name equation. It's not a conditional equation. Set it equal to 0. Good. We know when the meatball hits the ground, it is 0 feet above the ground, right? So you set it equal to 0, and now you solve for t. So here we go. Negative 2.66 t squared equals negative 3.2. T is going to equal plus or minus the square root of 3.2 over 2.66. Okay. Now, we always consider plus or minus when we extract the square root. But in this case, do we want the negative t? No, because that would be going back in time. The meatball was not rolling onto the floor. Now, I'll go ahead and use a calculator for this, unless someone else has it, you number sense people. If you can get this without a calculator, we have that meeting tomorrow at 7:30. Okay? So, flip this around. Oops. Oh, no. Where'd the meatball go? You get it, Kevin? No. Okay. I got it. T equals, we don't want the negative, so 1.096816994. And it's probably going to go on forever. So here we are now at the conversation of, if it's not a terminating decimal, how many decimal places are you responsible for reporting? 3. Always 3. And you can round or truncate. Of course, truncating means what? Not rounding. Good. 1.096 or 1.097. Okay, either one. Again, I'm a fan of truncating. On your numerical answer, then, you always want to put units. What are the units of t? Seconds. So in just over a full second, that meatball is on the moon's floor, okay, or in the restaurant. Now, this follow-up. How fast was the meatball traveling when it hit the ground? Very fast. Okay, is that what you want to write? No. We want the instantaneous velocity 1.09 seconds after it left the table. So how do you find instantaneous velocity if you have the instantaneous position? Derivative. So here we go. H prime of t. Now, here's the other thing you could do. H prime of t is good enough, but it has meaning, right? What are we going to call H prime of t? V of t. It's the instantaneous velocity. And so what is negative 2.66 times 2? Negative 5.32. T to the first. plus what? Nothing, plus 0. And now that I have B of t or H prime of t, now I can say either H prime of or V of, I'll use V of, 1.096. Now, here's the thing. Do I actually want to type in negative 5.32 times 1.096? Do I want to use this rounded number? No. Never, ever, ever do you use a rounded number for a subsequent calculation. So what I do is either realize it's still in my calculator on the previous line, or I like to store it as alpha A. So alpha A. So now I can just hit negative 5.32 times alpha A, and I get just a little bit larger magnitude, negative 5.8350. So 835. And what are the units of velocity? Feet per second. Remember, it's the derivative. So in Leibniz notation, it would be dH dt. And so what I like about Leibniz notation, the rate of change of the height with respect to time, is it preserves the ratio. So the units of h are feet, the units of times are seconds. So you get feet per second. And when I say feet per second, I mean like divided by seconds, not like kitty cat per, right? Like feet per second. That's a different per. Any cat people in here? Cat people? Cat person? Yeah. All right. If you retrieved it within 5 seconds, would you still eat it? You would? Yeah, and space is pretty clean. Yeah, because the dust particles don't fall to the ground as fast. If I paid for it, I'm probably going to eat it. I don't care if it's been 10 seconds. So anyway, that's just a whatever. That's a morals question. You don't have to answer that out loud. Kevin volunteered. Did you know that recently, just like last week, they did a scientific study, and they actually said, this is funny, that the 5-second rule doesn't really work, that there is no 5-second rule. Yeah. So, and it's like, really, we need science to tell us that? That's just kind of like how we justify that as soon as it hits the ground, it's just as nasty as if it were there for 10 seconds. If you can catch it just before it hits the ground. But then you're going to have a palm or whatever you catch it with that supports 5.835 feet per second. And being a meatball, it's probably going to go goose.
Is the floor really that dirty? Sometimes people's hands are dirty.
Oh, you're right. Maybe if you just drop that onto a dog's tongue, that's the most sterile thing. All right, part B. Using the given equation. I don't know how y'all get me so off task. Using the given equation, determine how many times stronger the acceleration due to gravity on Earth is than on the moon. Yeah, okay, so the acceleration due to gravity is approximately, we'll say approximately, 9.8 meters per second squared. But because we're talking about feet, we do the conversion, and it's about 32 feet per second squared. Okay, about 32. So how can I figure out what the acceleration due to gravity on the moon is? Yeah, remember, this is a true story, so we can actually use the equations we have. So V prime of t, which if you want, you could just call H double prime of t, and we're going to call it A of t. So there it is. There's your kinematic equations for all falling objects, how they're related to each other, higher order derivatives. It's going to be the derivative of negative 5.32 times t, which is what? Negative 5.32 feet per second per second. And the negative means that the velocity is decreasing, okay? So every second that passes, the velocity is going to gain a magnitude unit of 5.32 feet per second every second. So how are we going to use that to determine how many times stronger? I guess we could put negatives in here. Whether or not you say it's negative or not, it's a magnitude. You can divide, right? Now notice that I still have my 5.32 whatever stored in my calculator. Oh, no, that's the terminating decimal. Sorry, 5.32. So I'll just take what? 32 divided by positive 5.32. Good. So let's see, we'll do 32. You always want to show what we're doing, divided by 5.32, and that comes out to be about 6.015. So for all practical purposes, somewhere around 6 times stronger. So a lot of people think, or misthink, maybe not y'all, that there's zero gravity on the moon, but that's not true. There's gravity on the moon. Your meatball will hit the floor, but it's a sixth of what it is on planet Earth. Okay, so part C, based upon your answer to B, determine what your weight on the moon would be. Diet problem solved? Yes. All right, so you do yours and I'll do mine. Now, I'm going to store that 6.015, I'm going to store that as alpha B. Okay, and if I store it as alpha B, I'm going to write it here. So, you don't have to write your weight down. I'll write mine down, but you don't have to see what it is.
What is B?
Oh, I stored that as B, 6.015. Yeah. Yeah. You do yours, I'll do mine. I'll even round up here. I can afford to. LBS. Libras. That's what it's short for. Pounds. Libras. Libras to scale. Yeah. So anyway, yeah, diet problem solved. Still doesn't help your pants fit any better, right?
Makes you feel better.
You're lighter, right? You're lighter. I like that scale. Maybe you can go to like Sharper Image and buy a lunar scale.
If I'm on the moon,
And put it on your Earth bathroom, and it'll do the conversions for you. It's like, well, at least I'm 33 on the moon.
you can pick up huge things on the moon.
Yes, like an ant. You're like an ant on the moon. You're like an ant on the moon.
I've never
Okay.
thought about that. I can pick up huge things.
Just be careful. If you weigh less than 200.1, and that 0.1 was that cupcake I had. I'm sorry. You have to be careful though for strong winds on the moon, right?
Really?
Well.
What if I was like one?
The wind isn't on the moon.
Oh yeah, yeah. Dang it, Mr. Murphy.
Okay. Remember, the food is great.
Keep me on the video.
The food is great. But there's no atmosphere. Okay. Anyway, we're done. Let's talk about the test. Okay.